Hello friends, welcome to Power Electronics. Today we will discuss the average on-state current remaining part. In the previous class, we have discussed that consider an continuous DC current OA, which is denoted by IDC, that is anode current. And also in the dotted line, it shows the final temperature, whose junction temperature is 125 degrees Celsius. Also, we have taken a rectangular waveform whose amplitude is twice of the anode current. Here, due to overcurrent, it rises so fast that it passes the junction temperature 125 degree Celsius. So, what methods we apply to reduce this? Although it can damage the device. So, in order to limit the temperature to a 125 degree Celsius, first provide better cooling to the thyristor. Second, reduce the pulse amplitude. So, we reduce the pulse amplitude from OC to OD. When we reduce it, the amplitude, the junction temperature remains in the limit. Decrease in the amplitude of rectangular waveform would result in the lower anode current. So temperature remains in the limit. So our device won't get damaged. If we calculate here, the PAV is the average on-state power loss. Its formula is calculated by power forward on-state voltage across a thyristor into on average on-state current. More accurately, we can calculate it by 1 upon time period into instantaneous voltage across the SCR into instantaneous current, where T is the periodic time of the anode current waveform. RMS current for an SCR is constant, whatever be the conduction angle. How do we calculate the average current? Average current, here we calculate it by the I RMS upon the form factor. Form factor which is different for different waveforms. So we have taken in the diagram the two, that one is the conduction angle for the rectangular waveform and another is conduction angle for half wave sinusoidal. We will check for different conduction angles what are the this power loss and also the current, which is in amperes on average on state current. If you can see in the diagram that for an conduction angle 180, let's us we take a conduction angle 180 degree. Here if we check the anode current is less in B figure. You can see if we take here, it is approximately 130. Also if we take a line, we can get it for 150. So the anode current here is less in figure B for a half wave sinusoidal and more for the conduction angle for a rectangular waveform. Also, we can see the average on-state power loss, that is it rises up to 240 if we take for conduction angle 180 degree. If we saw it for half wave sinusoidal, it is approximately 210. So curves shown here are supplied by the manufacturer. All the specifications are given by the manufacturer so that user can use accordingly, with frequency range 50 Hz to 400 Hz. Let us take an conduction angle 30 degrees Celsius. How do we calculate the first of all conduction angle? We can calculate this conduction angle by area upon time period. Here the area is how many times that rectangular waveform has conducted. It is T upon its time period 2T into 360. So what we got here is that 180 degree conduction angle. This is how we calculate the conduction angle. Let us take a conduction angle 30 degree. What we get, the average on state current, that is IDC upon form factor. We have to calculate IDC, that is anode current, upon the form factor, which we get from the values. This is the form factor table for sine waveform. It is also for the, it is only for the pure resistive waveform. For the inductor, its value changes, so it is different for that. Here you can see the different values. For 15 degree, what is the conduction angle is 5.650. For 30 degree, it is different. As the conduction angle rises, you can also observe that the form factor value decreases. RMS on state current. We know what is an RMS value. RMS value is that first we'll take the square, then we take its mean, then its root. For an DC value, the RMS value and the average value is approximately same. If we take a conduction angle for 180 degrees Celsius, the form factor for half wave sine wave is pi by 2. But we have taken it for average value. We always consider the average value, that the thyristor circuit should be designed so that it can take the average current. Average current is 2 IDC upon pi instead of IDC. SCR derating below DC value. We will calculate by minus it by anode current minus the average on state current. So we get a value. Form factor value is always greater than 1. But for rectangular wave it is less than 1. Rectangular wave form factor is always less when as compared with the sine wave. Significance of I on state, average current and IRMS. RMS current, let if we have taken 35 ampere, then on state current, average on state current is that the we know the formula. The formula is divide the current by the this form factor. When we divide it, we get a value 18.67 ampere for the conduction angle 120 degrees Celsius. Now, if an ammeter is placed in the series with an SCR for measuring the average current, we get the same value 18.637. But if the conduction angle is reduced to 30 degrees Celsius, we won't get the same RMS current. We have to multiply this average on state current multiply by the form factor for 30 degrees Celsius that we have got it from the previous table. Here you will consider that for a half wave sinusoidal the form factor value is different and for a rectangular value is different. Here we will multiply, we will get 74.196 the RMS current, which is very higher, 3 to 4 times higher than average current. It can damage SCR very easily because if current rises in a very short span, it can damage the devices by increasing the junction temperature. So reason for damaging of SCR is the ohmic losses. Ohmic losses increases when the IRMS current passes. So current rating of on-state average current and RMS current are for the repetitive types. Depends upon the maximum junction temperature. So we should provide better cooling to the thyristor for its safe conduction. Again we reach at that particular point that we have discussed in the start, that we have two options to limit. First, to provide better cooling to the thyristor and reduce the pulse amplitude. In the second step, we have reduced the pulse amplitude so the temperature stay in the limit. So here the anode current remains in the final temperature remains at the junction 125 degrees Celsius. If it surpass to the 125 degrees Celsius, the temperature is so much that it can damage our SCR. So we will consider it. Thank you very much.